this lecture, we'll study the power transmission in rectangular waveguide. A rectangular waveguide is a hollow metallic tube of rectangular cross section in which the wave is propagating in one of the direction. In this course, we have studied this rectangular waveguide and we have considered that wave is propagating in this positive z direction. And in our earlier lectures, we studied what are T mode, TM mode, and we measured the electric field and magnetic components in both TE and TM mode. So when we consider this rectangular waveguide, we consider that the electric field and magnetic field are created within it and they used to propagate within this waveguide. We consider that wave is propagating in positive z direction. So since this electric field and magnetic field are propagating in the waveguide, we can assume that there is power associated due to propagation of electric and magnetic field components along the waveguide. There is power associated with them. So in order to measure the power transmission in rectangular waveguide, mathematically we need to first measure the power density in axial direction, because we are considering the wave is propagating in this axial direction. So in order to measure the power transmission in rectangular waveguide, power density in axial direction must be measured first. So in general, what is power density? First we'll see what is power density and then we'll see what is axial direction of that power density. So in your earlier course, you might have studied about pointing theorem. Through pointing theorem, we used to measure the pointing vector, which is actually the power density. It is denoted by S is equal to E cross of H conjugate. The average power density is measured as 1 by 2 real part of E cross of H conjugate. This is the power density. How it is a power density? E is in volts per meter, H is in ampere per meter. So E cross of H conjugate will be volt ampere per meter square, means watt per meter square. It is power density, power per meter square, power density. So this S is power density and it is a vector quantity, means it will have all x, y and z components. So let's write all the components. Sx ax plus sy ay plus sz az. Ax, ay, az are the unity vectors in x, y and z direction. Since in this case we consider that wave is propagating in positive z direction, means axial direction along the waveguide will be the z direction, means the axial component of power density is this. Axial power density in waveguide. For this particular case, please remember, if you consider that wave is propagating in x direction, then the axial component will be sx. If the wave is propagating in y direction, then axial component of power density that you need to measure for power transmission in waveguide will be syay. We are considering for this whole course that wave is propagating in positive z direction. That's why we are measuring this component here. So the axial directed power density for any mode, Smn represents any mode, Mn mode, either TE or TM, Smn Z is equal to Sz Az. So how do you measure Sz component? So let's measure. We know that S is equal to E cross of H conjugate. we are not considering, let's consider again real E cross of H conjugate. So this part will be only this part, Ax, Ay, Az, Ex, Ey, Ez, Hx conjugate, Hy conjugate, Hz conjugate is equal to Z component only. We require Z component only. So let's see what it will be. Ex Hy conjugate minus Ey Hx conjugate. Ex Hy conjugate minus Ey Hx conjugate. So it is equal to 1 by 2 real part of Ex Hy conjugate minus Ey Hx conjugate. Let's not write Az component because we have already denoted Z here. So the power transmission along the waveguide would be measured by measuring the power density along Z direction. So how do you measure the power transmission? This is power density. So power flow along the waveguide. Waveguide will be measured by integrating the axial component of power density over the cross section of waveguide. So the power flow along the waveguide, it will be represented as PTR is equal to power density axial component over the cross section area. Okay, this is surface integral. So power transmission along the waveguide is measured by integrating the axial component of power density over the cross section of waveguide. The cross section of waveguide will be the z directed z direction of the area. So total area is will have, it is also a vector quantity. So it also have all three components, dx dy az plus dy dz ax plus dx dz ay. This is y component of area, x component of area, z component of area. Okay. So we require only z component of area, that then only we could take the dot product here. So the power transmission along the waveguide is surface integral Smnz dot dx dy. Let's put the value of Sm and Z from this equation. Let's give it equation number 1. So PTR is equal to 1 by 2 real part of surface integral Ex Hy conjugate minus Ey Hx conjugate dx dy. Now let's further simplify this equation. How we can simplify this equation? By using the value of Zg. What is Zg? Zg is waveguide impedance. Guide impedance, which is defined as the ratio of transverse component of electric field and magnetic field. Hx over Ex over Hy is equal to minus Ey over Hx, or you may, if you have Z component, to Ey over Hz. See, we are following the right hand convention, means from X to Y to Z is positive convention. If you follow any other convention, then it will be a negative convention. So X to Y positive is here. Y to X is a negative convention. That's why negative is appearing in this equation. Y to Z is a positive convention. That's why it is a positive equation. If Ez over Hy would be written minus Ez over Hy. Z to Y is a negative convention, so negative appears here. So whichever component is available to you, you can measure the guide impedance like this by taking the ratio of transverse component of electric and magnetic field. Okay, so by using this equation, we have Ex Hy, Ey Hx. So we'll use these equations only. So PTR will become 1 by 2 surface integral. So this equation will become real. We are putting the value of Ex Hy here. Ex Hy conjugate is Ex conjugate divided by Zg. You can put conjugate here. We'll see that it's a real quantity later. Minus Ey. Hx conjugate is minus Ey conjugate divided by Zg conjugate. Dx dy. So PTR will become, why Zg is a real quantity? If you use TE equation of impedance, it is equal to eta over under root 1 minus Fc by F whole square. Eta is 377 ohms and Zg for Tm is eta under root 1 minus Fc by F whole square. So Zg conjugate will actually be Zg. It will come out of this equation, and Ex dot of Ex conjugate will be mod of Ex square. So this equation will become PTR. PTR is equal to 1 by 2 Zg surface integral mod of Ex square plus mod of Ey square dx dy. Similarly, if you put the value of Ex there, value of Ex from this equation to this equation, from this to this, you will get the equation in terms of H only, which will be equal to, it's simple, so I am writing it directly. PTR is equal to Zg by 2 surface integral mod of Ex square plus mod of Hx. It will be, let's write it again. It will be H PTR is equal to Zg by 2 surface integral mod of Hx square plus mod of Hy square dx dy. Okay, so if you have electric field components given in your equation, you can use this equation, and if magnetic field components are given to you, you can use this equation. So power transmission along the waveguide could be measured this way. So what will happen if you are asked to determine the total power transmission within the waveguide for all the modes associated within the waveguide? The total power could be measured as P total for all the modes is equal to the summation of P TR Mn for TE mode plus M comma N PTR Mn for T. Means if you combine all the TM modes within the waveguide and measure the power associated with them, and the summation of all the power transmitted for due to TE mode within the waveguide, the summation of these two will give you the total power of wave inside the waveguide due to all the modes propagating within the waveguide. In general, what you could write for PTR, the value of PTR that you may find in book is equal to Zg by 2 surface integral mod of h t square dA, or PTR 1 by 2 Zg surface integral mod of Et square dA. Here dA is the axial component of the area which is associated with the tangential component of magnetic field and electric field in the waveguide. Okay, so if the wave is propagating in, let's say, x direction, for example, so dA will be for x direction dy dz, and mod of ht square will be mod of hy square plus mod of hz square. So this is the general equation, and example is this one. So in the next lecture, we'll see the attenuation associated within the waveguide due to lossy nature of conductors and lossy nature of dielectrics within the waveguide.